Hi guys, today we'll be doing a video on limits. For this video, I've split up this topic into four main parts. So firstly is the simple stuff, where I introduce the basic idea of a limit and where you can apply a limit. And then I move on to intermediate stuff, where I talk about the properties of limits and the squeeze theorem. After that, there will be the advanced stuff, where I introduce the more formal definition of a limit, as well as how we can prove using that definition. And finally, we talk about what even the point of limits is in calculus for things like differentiation and integration. All right, so let's start. So the basic idea of a limit is if I were to take a function, say for example, if I were to take the very simple function y equals x. So this is the function y equals x. And if I were to take the point at x equals 2, and I want to find the value of this function at x equals 2. So quite obviously the value is 2 because if x equals 2 and y equals x, then y is equal to 2. But let's say I didn't know that. Okay, let's zoom into this part of the function. If I want to find the value of the output at this point, something that could be really helpful is to look at the output of the function for neighboring points, right? So let's start with 1. So from 1, we can kind of move towards 2. So hopefully we can get an understanding of what kind of value the function approaches as we get closer to this target value of 2. So f1 equals 1, f1.9 equals 1.9, and so on, right? In fact, we can keep going. We can put as many 9s as we want, and it will output the same value, right? So now instead of 1, let's say we start from 3, and we make our way down. So we kind of squeeze in this value too, based off of the values before it and after it. So if we do 3, then we do 2.1, then if we do 2.01, and then we do 2.00 dot 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 1, we get the same thing, right? And quite obviously, you can see that there's only one value that kind of fits this slot in the middle, right? And that would be f2 equals 2, right? This is the kind of value it approaches from the left and the right side. So we call this the limit of the function as x approaches 2. So how we would write that using the standard notation, it's limit or lim as x approaches 2 of x is equal to 2. Now notice that we squeezed it in from the left and the right hand side. So this is a two-sided limit. And for most standard definitions, a two-sided limit will be the regular limit. However, if you notice, right, we squeeze the function from the left-hand side and the right-hand side. So technically, we use two limits here, two one-sided limits, right? So from the left-hand side, we did these calculations, right? We tried to find the value of f2 from values that were smaller than 2, and we made our way closer and closer to 2. So this is the left-handed limit, and we call it left-handed because we start from the left-hand side and we move our way to the right. So we say that the limit as x approaches 2 from the left-hand side, we use negative because negative is on the left, right, of x is equal to 2. And likewise, for the other set of values, we used values greater than 2 and made our way down. So this is x approaching 2 from the right-hand side. So notice that the combination of these two, left-handed and right-handed limits, give you the standard limit. So this is left-handed, and this is right-handed. There are two more types of limits. and they both involve the use of this concept, infinity, right? Infinity is not a number. Um, Even though it seems very convenient to treat it as a number, it's actually not a number because for any number that you can think of, infinity is defined as like the largest possible number, but there is no such number because for every number that you think of, there will be a bigger number. You can just add one to it, you can multiply by two, and you'll get a bigger number. So infinity is a concept more than a number. And there are there are ways we can use this in limits. Uh, so for example, if I were to take the function y equals 1 over x, all right, and we can see that there are two asymptotes, right? There is the horizontal asymptote at y equals 0, and there is the vertical asymptote at x equals 0. So let's take the horizontal asymptote as an example first. So we see that this function uh, kind of approaches 0, but not quite. And the definition of an asymptote would be when the function never reaches that value, right, as it approaches infinity, right? So we can define this using a limit. So we say that the limit as x approaches infinity of 1 over x gives you 0. Likewise, we can do the same thing with the vertical asymptote, except this time it's a bit different. So if we were to take, for example, the right-handed limit as uh, x approaches 0 of 1 over x, we get positive infinity. Okay, this is particularly interesting because, um, as you can see, if you took the left-handed limit instead, what you would get is not positive but rather negative infinity, which makes sense because for infinitely small negative values, you'll get infinitely large negative reciprocal, right? And same thing for positive values, except the sign is flipped, right? So because of this, right, because the left hand and the right hand do not equate to each other, right, we say that a limit here for x approaching 0 does not exist. So it does not exist, or DNE. There are other examples in which a function's limit does not exist for a function. For example, if we were to take the limit of this function, y equals square root x, right? If we were to take the limit as x approaches 0, you might think that approaches 0, right? And that would make sense because the right-handed limit approaches 0. And in fact, if you just substituted 0 into x, you would get square root of 0, which is 0. But notice that there is nothing on the left-hand side. This is because the square root function is undefined for negative values of x. So that means that there is no left-handed limit. So because there is no left-handed limit, you cannot properly define a two-sided limit, which is why this is not true. The limit just does not exist. Another example of this, a similar, another example of a limit that doesn't exist would be, for example, the function y equals sine 1 over x, right? So it kind of looks like this. Yeah, and sorry, the drawing is quite bad, but the idea is that if you want to find the limit of sine 1 over x as x approaches 0, it's very difficult. And in fact, you'll find that it's impossible to find such a value because as you get closer and closer, as you zoom in to the graph, you can use like a software to do it. You'll find that it just keeps fluctuating, right? So it never truly like stops at a value. It just keeps going. And because sine oscillates from 1 to negative 1, you'll just get an entire range of values from 1 to -1, and you wouldn't know where it stops when it reaches 0. So because of that, this limit also does not exist. All right, let's look at one more type. Uh, let's look at the function y equals 1 over x squared. For this one, it's a bit more tame than the other functions. As x approaches 0, you can kind of say that it approaches positive infinity. However, remember that infinity is not a number. Infinity is a concept. So this technically doesn't meet this definition of like a limit in the rigorous sense, because a limit approaches a finite number and infinity is just not that. So this is technically a limit that does not exist, but it's very convenient to use this shorthand of positive infinity to denote this limit. So for the purposes of simplicity, I'll just say it's positive infinity. All right, so let's look at a few types of discontinuities. So you might wonder what a discontinuity is, and I'll just give you a very simple example. Say I had a function that looked like this. At this point, right, the function is discontinuous. So what that means is basically there is no smooth line connecting these two things. They're kind of just floating over each other. So this is what a discontinuous function looks like. And it's quite intuitive to understand, I guess, like discontinuities. This example in particular is a jump discontinuity. And jump discontinuities do occur in more definite functions. Like, for example, y equals modulus x over x. At the negative values is -1, and at the positive values is +1. So because of that, there's a sort of jump discontinuity at 0. So the limit as x approaches 0 of this function does not exist. And you can see because the left-handed limit and the right-handed limit don't equate to each other, right? So in the case of jump discontinuities, there is no limit at the discontinuity. Another example would be the infinite discontinuity. So remember, for example, how I was talking about y equals 1 over x squared, and looks like this. This is infinite discontinuity. And why it's a discontinuity is because while I can ascribe a value of infinity, the truth is it never really reaches infinity. Infinity is not something you can reach. So even at the so-called top, there will still be some gap between them. Like that is the nature of an asymptote, is that you'll never be able to reach that value. So this is an infinite discontinuity. And finally is a discontinuity that can actually have a limit. All right, take for example this function, y equals x plus 1. All right, so this is a nice, neat function, and it's definitely continuous because at every point, there's no like jumps, there's no gaps, there's no infinite asymptotes. But if I were to take this function and instead of x plus 1, I were to turn it into, I were to multiply x plus 1 by x minus 1, and then divide it by x minus 1 again. So x plus 1, x minus 1, divided by x minus 1, and then simplify it, right? It's the same function, but there is one key difference. The function is undefined at x equals 1. And you can see why, right? Because the denominator cannot equal to 0. So there is a discontinuity here. This is called a removable discontinuity. And why it's called a removable discontinuity is because you can just simplify the function and the discontinuity will disappear. So there does exist a limit as it approaches 1. And in fact, the limit is 2, right? Because if you just took the original function and you substituted x equals 1, you would get 2. So now let's move on to the indeterminate forms. There are 7 indeterminate forms. There's 0 divided by 0, infinity divided by infinity, infinity minus infinity, 0 to the power of 0, 0 times infinity, infinity to the power of 0, and 1 to the power of infinity. Okay, so let's start with 0 divided by 0. So there are many cases where you would find this kind of indeterminate form. So for example, let's take the limit as x approaches 0 of x squared divided by x. Quite obviously this is x. I mean, this is 0 because when you divide x squared by x, you would get x. And when x is 0, x is 0. So this is quite simple. But there are other examples where it doesn't equal the same thing. So let's say I were to take that again, but flip it, right? Then this would be the same thing as 1 over x, for which we know that there does not exist a limit, right? So next one would be infinity divided by infinity. Similar to the one above. Say for example we have 2x divided by x, and we're trying to take the limit as x approaches infinity. So if we do some simplification, it's quite obviously 2. But of course, the same argument can apply to, for example, 5x divided by x, right? And then in this case it would be 5. So the thing about indeterminate forms is that they're indeterminate not because you can't find a solution, but because the solution is different depending on what functions are involved. So the next example would be infinity divided by infinity, which, as you can see, for example, limit as x approaches 0 of 1 over x minus 1 over x squared would give you the limit of, if we cross multiply, we get x minus 1 divided by x squared. And you will find that this value is negative infinity because for small positive values of x, because of that negative 1, the function will be negative. And then for arbitrarily small negative values of x, it will still be negative because the x squared value on the bottom is always positive and the top will just be more negative, right? So it approaches negative infinity either way. All right, the next one is 0 to the power of 0. And we'll take, for example, the function limit as x approaches 0 of x to the power of 0. So as you know, x to the power of 0 is always equal to 1. So this is quite obviously 1, right? But if I were to take instead 0 to the power of x, 0 to the power of x is 0, so it will be 0. And then next, moving on to 0 times infinity, we will have some limits that take this form, like x times ln x, the right-handed limit. And I'll just say that it's 0, like without any proof. But you can figure it out using techniques that I will explain later. And then we have infinity to the power of 0. So you can take the limit as x approaches infinity of x to the power of 1 over x. And this is actually 1. I will also not explain, but later you can figure out why. And lastly, we have 1 to the power of infinity. So take a guess as to what this value is going to be. If you answered E, you are correct. So this value is approximately 2.71828. And it's actually Euler's number, right? It's a pretty interesting result. And in fact, it's one of the definitions as well, I think, for Euler's number. All right, so now let's move on to some practice questions. All right, so I'll give you 3 practice questions, and I'll give you some time to do it. you can pause the video if you want to get some time to do it yourself. Otherwise, I will go through it pretty quickly. All right, and the last one. Okay, so I will give you 5 seconds to do it. Okay, so let's start with the first one. The first one is quite easy. So if you just substituted x equals 2, you would just get the answer straight away. So you would get 2 squared minus 2 cubed, 4 minus 8, negative 4. For the second one, it takes a bit of factorization, but it's also nothing too complicated. It's x plus 3, x minus 1, divided by x plus 3, x minus 3. And you'll find that you can actually cancel out these two. The same thing. So if you substitute it, x equals negative 3, after that, you would get negative 4 divided by negative 6, which can be simplified to 2 divided by 3. And lastly, this one has a square root, so it's a bit tricky, but you can just realize the denominator. So you can multiply it by its conjugate. And what you'll find is that the denominator simplifies very neatly into 1 squared minus x minus 1 squared, which is equal to 1 minus bracket x minus 1, which is 2 minus x, which cancels out by the top. So what you get is 1 plus square root x minus 1, and if you substitute in x equals 2, you'll just get 1 plus square root 2 minus 1, which is equal to 2. All right, now let's move on to the intermediate stuff. So properties of limits. As with any kind of function or process or whatever, there are certain rules that you have to follow. And just like exponentials or logarithms or surds, right? Limits also have their own rules. So let's start with the. All right, let's use a general sort of limit. Okay, limit as x approaches c of fx equals L. This is generally what a limit looks like. So if I were to, let's start with the constant rule. So in this case, fx would be equal to some constant k. And quite obviously, the limit is k because the limit is not because the function is not dependent on x. And if you drew y equals k and then you looked for that point c, then you can convince yourself pretty easily that the limit is k. All right, so the next one would be the constant multiple rule. And basically what it's saying is that if you have a constant multiple of a function, k of fx, it's basically the same thing as having that k times of the limit itself. So this is also pretty easy to kind of see. Like if you had a function that looks something like this, and your limit at this point is L, and then you scale that function by k times. Yeah, you would get something like this, and then this would be k of L, right? So this is not that difficult to see. All right, next would be the addition. addition rule, where if you take the limit of the sum of two functions, you can essentially split that limit between those two functions. So this is, I mean, it's kind of like adding two functions together, right? And then at a certain point, the limit of the function of that sum would just be the sum of those two limits. So this goes with the same goes for differences. And in fact, most of these rules are actually quite easy to follow. There is the product rule, where the limit of the product of two functions is the same thing as taking the product of the limits of the two functions. And then there is also the quotient rule. And it's the same thing. The only catch is that the limit of the denominator function cannot be 0. Because otherwise that would be division by 0. And then we also have the power rule, which is just an extension of the product rule, but if you were to multiply the function by itself. And lastly, we will have the root rule, I think, which is the same thing as well. It's an extension of the power rule. All right, so now that these rules are out of the way, I want to talk about a very interesting theorem. So this is called the squeeze theorem. It's also called the sandwich theorem. But basically, what it's trying to get at is that if you have three functions, okay, if you have fx, gx, and hx, and they are related by this. Basically, if gx is bound by fx and hx as an upper and a lower bound, right? What it states is that if the limit of fx equals to the limit of hx at one point, then that is then the limit of gx at that point will also be the same limit. And you can kind of illustrate it like this, right? If I were to have a function gx, and then I were to have a function fx that looks something like this, and then I were to have another function hx, right? Basically at this point, right, this is the C, and this is L, right? I mean, basically they squeeze it at that point, and so the limit will be the same. So, okay, now that we know these properties as well as the squeeze theorem, I would like us to take a look at these three questions. Yep. So I will give y'all some time to solve these questions. You can pause the video here if you want. So try to find the answer to these three questions. I will give you 5 seconds. Okay, fantastic. So for the first one, it's not a difficult question, but I wanted to show how we can use the properties of the limits to solve it. So I will be quite thorough with my usage of these properties. So firstly, we can see that it's a sum of two functions, right? So we can split up the limit. Okay, and then now we can see that for the first limit, it's a fraction. So we can kind of bring the limit into the fraction. This is the quotient rule. And then we can use the root rule for the next one to bring the limit inside the root. And then we can see that the top is also a sum, so we can use the sum rule, the addition rule as well. And then at the bottom, it's a power, so we can bring it inside using the power rule. So over here, we can split it up again because it's a difference, right? So we have limit as x approaches 3 of x minus the limit for 2. And then we can and then we can look at the first limit again. And we notice that it's x squared. So we can bring the limit inside and then square it. And then we can use the constant rule. So the limit of 2 is just 2, right? Regardless of x. And we can, since this is a difference, we can also kind of split it up again. Sorry. The limit of as x approaches 3 of x is just 3. And the limit for 2 is just 2. All right, and then lastly, we have the limit of x as x approaches 3. That's obviously 3. 3 squared plus 2 divided by, again, 3 minus 1 to the power of 5 plus cube root of 1 gives you 11 divided by 32 plus 1, which is 43 divided by 32. All right, let me move this down a bit. In fact, let me move this one down a bit. All right, so next question. This next question is a squeeze theorem question. So what we can notice is that sine 1 over x, remember, it's one of those functions that doesn't have a limit as x approaches 0. But the presence of the x squared can actually help. So let's say, so because sine oscillates between -1 and 1, we know that this is true, right? We know that sine 1 over x is bound by -1 and +1. So if we multiply it by something that we know to be positive, in this case, x squared, right, we will get this. And in fact, we already have the function that we're trying to find the limit of in the middle. So if we were to take the limit of all of the functions, we'll actually find that the limit, of the functions that are bounding it on the left and the right are actually 0, right? Because, I mean, it's quite obvious. So using the squeeze theorem, we have figured out that, I mean, there's only one value between 0 and 0 inclusive, right? And that is 0, right? Therefore, the answer is 0. And it's actually a very nice application of the squeeze theorem to solve what would otherwise be really difficult to solve, right? And here's the last one. So this is very interesting. It's a very interesting proof. And for this one, I'm going to use geometry. This is still a squeeze theorem proof. So we have a circle, a unit circle in fact, and let's just say this angle is x. So we are trying to find sine x divided by x. All right, so where is sine on this circle, right? Because the hypotenuse of this right angle triangle is 1, sine x is simply the opposite side. And then the bottom would be cosine x, right? So we need to find two things that can bind sine x, right? So firstly, we notice that the arc length of this arc is given by the angle multiplied by the radius, right? X times 1, so it's x. And then we find that there is actually another arc we can use, which is the arc formed by the arc of radius cosine. So this is x cosine x. So because sine is bound by these two arcs, we can use the following inequality. So x cosine x is less or equal to sine x, which is less or equal to x. And if we divide everything by x, we find our function of interest in the middle, right? So if we take the limit of all of these functions as x approaches 0, we find a very interesting result. So the limit as x approaches 0 of cosine is 1, because cosine 0 is 1. And obviously, using the constant rule, the limit of 1 is just 1. So because of that, we can use the squeeze theorem to actually prove that sine x divided by x approaches 1. And this is a very interesting result because it is used in physics quite extensively. This is the small angle approximation for sine. And it makes use of the fact that the ratios between sine x and x approach 1 to 1 as the angles get arbitrarily small, up to 0. So this is a very interesting result. All right, so now is my attempt to explain the epsilon delta definition of a limit, which is my worst nightmare. So let's bring back the function y equals x, and in particular, x equals 2. So just now, I kind of briefly explained how we can kind of find f2 by inputting values that are close to 2 and then seeing what the output produces. So epsilon delta is kind of an attempt to formalize that idea. And it's quite a rigorous definition. Epsilon and delta are ultimately distances. And so delta is distance and epsilon is error. So within a certain distance of this target value 2, right, we want to see how the error epsilon changes. So as delta decreases, as we get closer and closer to 2, epsilon should also approach this limiting value, f2, right? So how we want to describe that is by using absolute value, right? Absolute values can tell you basically the distance, right? So let's bring in a limit as x approaches. In this case, it's 2, but let's just call it c of fx is equal to L, right? So x minus this target value, right? So basically, we are limiting the x values to within a distance delta of the target input value. And then, likewise, we are also limiting the output to within an error epsilon of the limit. So the idea is that for a given epsilon, right, as we squeeze the output, a limit will only exist if we are also squeezing the input for that given range of epsilon. So the formal definition of epsilon delta would be for all epsilon that's greater than 0, because distances are supposed to be greater than 0. There exists a delta that's greater than 0, such that when the distance between the output and the limit is lesser than epsilon, the distance between the input and the target value is less than delta. This is the very rigorous, very formal, very pure math definition of a limit. So let's try to apply in this case, okay? So our function is x, and the limiting value as x approaches 2 is 2. So how do we try to find this using the epsilon delta definition? So first we look at the fx. So fx is x, right? So x minus L, which is 2, is lesser than epsilon. Needs to imply that x minus c, which is 2, is lesser than delta. All right, so given an arbitrary value of epsilon, we need to find a delta such that this works. But if you look closely, we can see that you can actually set delta to be equal to epsilon, and this will work. This is a very simple case, right, of this definition. And so it's proven that if you use delta equals epsilon, this implication will hold true. But it's not always this simple, right? There are harder questions that involve epsilon delta. So for example, if we were to take the function y equals 1 over x at x equals 1, and we were to try to find limit as x approaches 1 of 1 over x equals to 1, right? We need to prove that this is true. So we can pull out epsilon delta definition of a limit. So for all epsilon greater than 0, there exists a delta greater than 0 such that when fx minus L is lesser than epsilon, x minus c is lesser than delta. So in this case, first we find c. C is 1, and L is also 1. So fx is 1 over x. So 1 over x minus 1 is less than epsilon. Needs to imply that x minus 1 is lesser than delta. All right, so we can expand this absolute value thing, because ultimately absolute value is just about the distance, right? So basically, when the function, is within e distance of 1, like that, we need to find a value that would suit this, right? So we can take the reciprocal. And because, okay, for this purpose, let's set e to be lesser than 1. So that means that 1 minus e is a positive number. So we can flip it over without worrying too much. Just flip over the sign. And now we have this, right? We can subtract 1 to get the same kind of expression in the absolute value. And now what we need to do is we need to try to find a delta such that we can contain this x minus 1. So what we notice is that obviously this is a positive number, right? But this is a negative number. And why this is a negative number is because since epsilon is less than 1, but it's still a positive number. It's greater than 0 because we established that in the definition, right? That means that this value is definitely less than 0. So this is negative, this is positive. So we can take delta as the smallest of these two. If we define delta to be the minimum of 1 over 1 minus epsilon minus 1 and 1 minus 1 over 1 plus epsilon, this is a valid delta. And in fact, this would be the answer. This would be the delta we need to prove that this limit does exist, right? So yeah, this is the answer. And we have proven using epsilon delta. Uh, Sorry, my proofs aren't very rigorous, but I think if they were any more complicated, I would not be able to do this. Yeah, so these limits, this definition of a limit is very useful for finite limits, right? But when it comes to infinite limits, we cannot use this definition. This definition only works for finite values of C and finite values of L. So for a limit at infinity, right, let us establish a different definition. So in this case, C is infinity, um, but we can't just replace the definition and then just put C equals infinity. Um, so the definition of epsilon delta, uh, for infinite values, we introduce this number n. Okay, so n is a very big number, and the idea is that we need to make it such that n is there'll always be a number greater than n for which we can get closer and closer to the actual value, right? So for every epsilon greater than 0, there exists a number n that is greater than 0, such that when like positive values of x are greater than n, uh, fx minus L is within an error distance epsilon. This seems like a very strange kind of definition. But if I were to look at, for example, the function, uh, very, very useful function 1 over x, right? Let's say I want to find the limit as x approaches infinity of 1 over x to be 0, right? Basically, what this definition is trying to say is that, uh, okay, so we see epsilon is like, okay, so we have 0 and we have epsilon, right? Basically here. Basically, when a positive number x is greater than n, so what they're trying to say is that let's say there's a very, very big number here, n. So there will always exist a positive number that will be bounded, whose output is bounded by this epsilon. So yeah, essentially n is containing uh this limit. And because n is so big, you'll always have bigger and bigger values of n until it goes to infinity. In this case, okay, fx is 1, minus L is 0, so it's just the absolute value of 1 over x. It's lesser than epsilon. Then we need to find this large number n such that this will work. Negative epsilon is lesser than 1 over x is lesser than x. If we were to take the reciprocal of these two, because epsilon is quite small, right? If we were to take the reciprocal, 1 over epsilon would be pretty large. All right, let's consider the case where 1 over x is positive. If 1 over x is positive, then x will be greater than 1 over epsilon. And if 1 over x is negative, then that means, since negative epsilon is lesser than 1 over x, that means positive epsilon will be greater than negative 1 over x. And then that means that negative, if you take 1 over epsilon will become smaller than negative x. Alright, but since we are dealing with positive values of x, right? And in fact, even here is a positive value because, I mean, we are assuming that x is negative, like 1 over x is negative. So basically, we can set our value n to be 1 over epsilon. And since epsilon is a tiny value, 1 over epsilon will be quite big. So yeah, this is proven, right? Another thing we can look at is the vertical asymptote, right? And this would be the infinite limit. So limit as x approaches some value c of fx is equal to infinity. All right, so because I want the function to be nice and neat, I'm going to use 1 over x squared instead. So you can definitively say it goes to positive infinity. In this case, we can kind of use the opposite of this. We can say that for all n greater than 0, there exists a delta greater than 0 such that when x minus c is within the range of delta, fx is greater than n. So it's like the same thing as the one above, but it's slightly different. Oh yeah, and for the one above, you can use a similar definition for negative infinity. But instead of positive x being greater than n, you can have like a negative x being less than n for some negative, really large negative number. So in this case, we are taking the limit as x approaches 0 of 1 over x squared being positive infinity. For all n, okay, so we need to find this value of n. No, we don't need to find this value of n. We need to find the value of d, right, delta. And so we need to find value of delta such that when x minus 0 is lesser than delta, 1 over x squared is greater than n. Alright, so we've established that 1 over x squared is greater than n. Now we need to prove that we can find this value of delta. So how we would do this is, alright, since n is like a positive number, right, we can kind of flip it over. And we'll get this. And in fact, this is the case that the x squared is like the absolute value of x squared as well. So you can actually find this to be 1 over the square root of n, and you can actually set delta equal to 1 over square root n. So this proves essentially that this basically proves it, right? You found a value of delta, which is quite small because n is a really big number, right? So yeah, this is the nature of epsilon delta proofs as well as proofs involving this n. So now I have a few fun questions for you. All right, so let's start off with prove this using epsilon delta. And then we have this one, which is quite interesting because I did not teach you how to solve this. And finally, prove this result. Okay, this one's a bit harder, so I'll give you 10 seconds. Okay, 10 seconds is up. So let's start with the first question. So for the first question, C is equal to 3, L is equal to 3. So we're trying to find, for all epsilon greater than 0, there exists a delta greater than 0 such that square root of 2x plus 3 minus 3 within epsilon implies x minus 3 within delta. So what we can do here is we can simplify this. And we can simplify it by sort of rationalizing in a kind of reverse way. So what we do is we realize the numerator, which is quite interesting. Of course, there are other ways to solve this, but this one is actually quite neat. So we get 2x plus 3 minus 3 squared, 2x minus 6 divided by this minus 3. Sorry, there's no minus 3. So what we notice is that we get 2 times of x minus 3, which is what we're trying to find. So because the square root of x plus 2x plus 3 is positive, right? This is actually less than just straight up 2x plus 3 divided by 3. Because the numerator is, or the denominator is smaller. So this is actually equivalent to 2 over 3 delta. So actually, if we set delta to be 3 over 2 epsilon, we found our answer. Alright, let me move the rest of these down. Alright, so for this next problem, what we have to do is take a combination of the two kind of infinite limits and limits at infinity kind of proofs. So for this case, I will use n and m to represent really large epsilon and really large delta. So for all n greater than 0, there exists m greater than 0 such that fx being greater than n implies x being greater than m. So for this case, we see that e to the x is greater than n. That means that x is greater than ln n. That was quite simple. We just take m is equal to ln n, and it's proven. Alright, for the last one, this is quite an interesting proof. And basically, what we are trying to show is that a limit cannot exist for sine 1 over x. So the idea behind this is that, alright, we try to find a value L, right? For all epsilon greater than 0, there must exist a delta greater than 0 such that blah blah blah, right? So we can substitute sine 1 over x minus some L has to be less than epsilon in order for x minus 0 to be lesser than delta. So to disprove this, we just need to prove that it doesn't work for a value of epsilon. So if I were to take, for example, epsilon equals 0.5, that means L minus 0.5 would be lesser than sine 1 over x, which is lesser than L plus 0.5. However, because sine 1 over x is a periodic function, for x between 0 and delta, it is only expected to cover this much of the interval, which is, I mean, if you put it on a number line, right, this covers a distance of 1. However, over this course, right, sine 1 over x will cover the set of 1 over delta lesser than 1 over x, which is lesser than infinity. So because it goes to infinity, it will quite obviously cover a lot of periods of 2 pi, which means that it will go from negative 1 to positive 1. So it contradicts with this, right? Because negative 1, positive 1, this covers a length of 2. You cannot restrict it to epsilon equals 0.5. And in fact, you cannot restrict it to a lot of values of epsilon, as long as that epsilon value is below 1. Therefore, because of this contradiction, right, it just does not exist. All right, so now quickly I'll go through the applications of limits in calculus. So let's say I want to find the slope of a function at a particular point. Right, what I would do usually is to take the slopes around the point, and then I would try to get as close a slope value as I can to get the instantaneous slope, right? Because usually, a slope follows formula y2 minus y1 over x2 minus x1. However, if you want to find the slope at an instantaneous point, you cannot, because if you tried to take at x, y, right, you get y minus y over x minus x, which is nothing, right? So, this obviously requires differentiation. And the definition of differentiation is actually given by a limit. It's the limit as x approaches, limit as h approaches 0 of fx plus h minus fx over h. So what is going on here, right? This is essentially the rise over run. If you have a function, if you zoom in really hard and you try to cover the rise over run for, let's say, value of x plus h, you would get fx and fx plus h. However, as you make this value of h smaller and smaller, it approaches the instantaneous rise over run. So that's why this is the first principle definition of a derivative. So a useful thing that comes with defining differentiation is that you can actually use it for limits, right? The limit of two functions, or like a fraction of two functions, is the same thing as that limit, the limit of their derivatives. This is called L'Hopital's rule. So we can also apply this to integration, which is anti-differentiation, right? If we wanted to take the area of a function using a bunch of rectangles, the idea here is that we try to make these rectangles pretty small, right? So for a given rectangle, let's zoom in on one of them. So the idea is that for a given kind of slice of this graph, at the value x, you have output fx, and value x plus h, you have output fx plus h. So the idea is to make this value of h as small as possible. So the definition of an integral, in particular a definite integral from a to b, is the limit as the number of slices approaches infinity of the sum as I goes from 0 to h of 1 over h times f a plus b minus a over h times I. So this is the limit definition of an integral. Yeah, so this is the end of the video. Hope you enjoyed and learned a little bit about limits. This is as much as I could think of. So yeah, hopefully it helped. Thank you for watching.